Okay, today we are going to talk a little bit about climate mechanisms or the mechanisms that create the climate patterns we see across the globe, and then talk about the biomes or define some biomes so that we can start linking the climate of a region with why that climate occurs there and what that vegetation is going to look like. So some of you have had this information before, have had pieces of this information before. So just a warning, some of it might be a bit of review, especially talking about the mechanisms for the climate variability we see around the globe. But I've had enough people in the past comment and appreciate this lecture in the detail I go into it, so I'm going to keep doing it until everybody seems really bored. So just a highlight of the types of terms we're going to talk about. You should recognize maybe all of these terms, if not most of them. But I think a lot of times we use these terms in academics, in natural resource management, and without a real clear idea of the quantitative definition. So I really like quantitatively defining things when we can, because that eliminates miscommunication. My goal today is to not only introduce you to the mechanisms, or at least review the mechanisms, but then give you the best definition I can find, quantitative definition for these different terms. So what I'm going to do is I'm going to start by talking about latitudinal variation in temperature, then I'm going to talk about the temporal variability in temperature, and then I'll talk about precipitation. And after each kind of section, then we'll talk about the actual terms you would use to describe a climate with a particular range of temperatures or particular variability, and kind of show you where that climate is distributed. So that'll be the format of this lecture. So let's just move forward. So right now we're going to talk about large spatial variability in temperature around the globe. So we know that the warmth of our planet comes from the fact that we're getting a lot of energy from the sun. And there's two factors that contribute to the variability, the latitudinal variability in temperature as sun hits the Earth. And these two, or one of them is referred to as beam spread, underlined here. And if you look at this picture, you can see these two bands of yellow here hitting Earth's surface. And these are supposed to represent solar radiation at different points on the Earth's surface. Where the solar radiation hits the Earth's surface near the equator, it's kind of like, it's perpendicular, right, or normal. So it's hitting it at pretty much right angles. So all of the radiation that is coming in this band is directly hitting Earth's surface, and so it's fairly concentrated. However, as that solar radiation hits further north and further south, that curvature of the Earth causes the solar radiation to be spread out over a larger area. And so in this picture, these two bands of solar radiation here are the same thickness. But you can kind of see that the one hitting at the North Pole, that band spreads out over a larger portion of Earth's surface. Now, the fact that both of these beams are the same thickness means they each have the same amount of energy in them. So this beam of light, or this band of solar radiation hitting the North Pole or near the North Pole, the energy in that band is spread out over a larger area. So each little unit of land, if we had a little, if this is a unit of land, in the north or near the North Pole, that unit of land is going to get less solar energy than that same unit of land near the equator. And so the fact that it's getting less energy means it's going to warm up less, and that creates one of our first ways that we get this temperature variability around the globe, is just beam spread, how that solar energy is spread out over Earth's surface. So it's spread out a lot as you move to the north and to the south poles, and it's spread out less as you move towards the equator. So here's just a map of temperature in the United States. This should make sense to you, where our warmer temperatures are more in the yellows and reds, and colder temperatures are blues to pinks and purples. And so you can see, of course, we know in the southern part of the US we have a lot warmer temperatures than we do in the northern part of the US. And so this gradient that we see here is partially created by this beam spread. Solar radiation is going to be spread out over a larger proportion of land in the northern part of the United States than in the southern part. Okay, the other factor is going to kind of be similar in its effect as you move to the north or to the south, but this is called atmospheric interaction, atmospheric interference. So what this is in Earth's atmosphere, this kind of, if we were to think about this bubble around the Earth being Earth's atmosphere, it's got lots of stuff in it. There's water vapor in there, there's dust particles, there's gases, there's all kinds of stuff in there that is absorbing the solar radiation. Some of it actually reflects it back towards the sun. Some of it re-radiates it as a different and lower wavelength, so less energy. So all of these processes that are happening reduce the amount of energy that is passing through Earth's atmosphere. So if we go back to this picture, again, this picture is really representing beam spread, and each of these yellow lines is showing a band of solar radiation. But you can imagine that when the solar radiation is passing through the atmosphere, when it's passing through the atmosphere in the north and the south, it's passing through at an angle. So if this is Earth's atmosphere, like the thickness of Earth's atmosphere, and you pass through it like directly, that path is relatively short than if you pass through it diagonally, right? And so the fact that solar radiation passes through the atmosphere diagonally means there's more chance for that atmospheric interference to occur. So there's more refraction and absorption and scattering of that energy. And so both beam spread and atmospheric scatter or atmospheric interference result because of the curvature of the Earth, and they both reduce the amount of energy that hits Earth's surface at the North Pole and the South Pole, or as you move away from the equator, the amount of energy gets less and less, creating again the the temperature gradients that we see. So I showed you the temperature gradients in US just a minute ago. Here's global patterns of solar radiation or solar energy inputs, and this is exactly what we would expect. It's fairly high near the equator and gets lower and lower as you move away from the equator towards the poles due to beam spread, atmospheric interference. Be comfortable, especially with beam spread. I mean, I think it's a fairly straightforward concept, but it comes into play several times throughout the semester, so just remember that one. So variability, spatial variability, or the spatial variability associated with latitude is driven primarily by beam spread and atmospheric interference. Let's talk briefly about seasonal changes, or the temporal patterns of temperature. You all know that Earth is kind of rotating on its axis, and that axis tilts throughout an annual cycle. So during the summer, the northern hemisphere is pointed closer or is angled toward the sun, and in the winter we're angled away from the sun, and the opposite is true for the southern hemisphere. And so here in this picture, on the top part of this picture, we're looking at the rays or solar radiation coming from the sun. And so you can see this center one, the one that's labeled vertical ray, is hitting directly perpendicular a little bit north of the equator. So that's where beam spread and atmospheric interference is the smallest, or has the smallest effect. But when that switches to winter, the most direct or kind of perpendicular spot that solar radiation is hitting Earth's surface is going to be south of the equator. And so this change in the amount of beam spread and interference is what causes these change in temperatures that we see throughout a season. Okay, so let's talk briefly about the terminology or the terms we would use to describe different temperature regimes or patterns we would see across the globe. So there's 5 we're going to talk about. There's tropical, maritime, temperate, continental, and polar. And so for all but one of these, I'll give you a quantitative definition that we can use in describing and talking about different climate patterns and different ecosystem types. So first is our tropical climate pattern. So these abbreviations should look familiar. They're from the Köppen climate system that we introduced last week, and you might have already done for your homework. But the definition, the quantitative definition for tropical climate is that the coldest month, the average temperature of the coldest month is greater than 18 degrees Celsius. So that just means there's never a cold time, right, in the tropics. So you can just see a distribution of tropical ecosystems here, and of course they're all going to be centered near the equator, where that beam spread and atmospheric interference is the smallest all year long. The other thing I want to point out here is that a lot of times I think we associate tropics with tropical rainforests that are really lush and get lots of moisture. But remember, there's lots of tropical places that are dry. There's seasonally dry tropical forests. There's tropical savannas that are drier than tropical forests. So tropics, remember, does not describe precipitation amounts or patterns. It only describes temperature. The next one is maritime. Oops, sorry. Maritime is the one that doesn't have a great quantitative definition because it can be either hot or it can be cold, but the variability between summer and winter is really small in a maritime climate. So it's going to be fairly uniform temperatures throughout the year, but it doesn't have to be warm. So as an example, if we look up here in Alaska, and kind of northern part of Canada, we've got maritime climates. I was hesitating because there's actually some maritime climates in the northern part of Alaska, and that's what I was going to point out, but it doesn't really show up on the map. But these areas have what we would call maritime climates, and it's because they're close to the ocean in this giant body of water, and that giant body of water acts as a heat sink. So in the winter, it releases some of its heat so that the air around it isn't as cold, and in the summer it absorbs some of the heat, and so those places don't get as hot, and so it buffers the temperature variability. But you can see there are places near the equator that still have a maritime climate, and places that are far north that have maritime climate. So it doesn't have to do with mean temperatures, it's just temperature variability that it's describing, and generally it's describing a place near the ocean, but you can see places on here that are quantified as a maritime climate that aren't right near a large body of water. So focus on the variability part for maritime climate. All right, temperate is the next term we're going to define. So a temperate climate, many of us probably live in kind of a temperate climate. A lot of people feel like we get a lot of folks coming from the Midwest or Northeast, which is more of a temperate climate as well. So lots of people in the US are familiar with this kind of climate pattern. The definition of temperate, I just lost my light. It's only my, fourth video this semester, so I'm still getting everything worked out. So I'm going to pause it, turn my light back on, and then we'll start up again. Okay, I'm back. Light's back on. I think the screen might have moved a bit, but ready to go again. Okay, temperate climate definition. The average temperature of the warmest month has to be above 10 degrees C, and the average temperature of the coldest month has to be between 0 and 18 degrees C. So relatively warm in the summer and cold, but not super cold in the winter. Most of the temperate climates are found between 23.5 and 66.5 degrees latitude. So, a little outside of that zone of kind of what we would think of the equatorial zone. Okay, let's go to the next one. Is continental. So this is going to be very similar to temperate. The average temperature of the warmest month has to be above 0 degrees Celsius. The difference between temperate and continental is how cold it gets in the winter. So the temperature of the coldest month has to get below freezing to be a continental climate. Continental climates are generally found in the interior of large land masses, so in the kind of center or interior of our continents. And so if you look at this map, let me move my picture here for a second. You can see we don't have any continental climates in the southern hemisphere, and that's because our large land masses in the southern hemisphere are close to the equator, and so we have much smaller land masses as you get to move away from the equator, and they're not large enough to create these continental climates. So continental climates are unique for the most part to the northern hemisphere. And then our last one describing temperature is polar. And the definition of that is just that the temperature of the warmest month is less than 10 degrees C. So it's never going to get very warm. Okay, so just want you to get some familiarity with thinking about, or I guess relating a graph of temperature to these terms. So I'm just going to, I guess you could pause it here for a second, take a look at these figures, and see which of those 5 terms would apply to each of these figures. So we've got maritime, we've got tropical, we've got temperate, we've got continental, and polar. So look at these and think about which term would describe these figures. All right, pause it. And then I'm going to give you the answers. So if you remember, the definition of tropical is that every month is above 18 degrees C. And this one, we don't have tick marks here, so it's hard to tell if it's exactly that. But this one, A, represents a tropical climate where it's always above 18 degrees Celsius. B then, so if we look at B in the warmest month, it's going to be above 10 degrees C. And or I guess, but in the wintertime, it's below 0 degrees C. So this fits the definition of a continental climate. C is quite similar, except for it doesn't get as cold. So its warmest month is above 10 degrees C, and its coldest month is hovering around 0, but not dipping below 0. So that would be a temperate climate. So these are the 2 most similar ones. And then D would be, you could probably say it could be polar or maritime, right? There's not near as much variability between summer and winter compared to these 2. B and C, but it's also always below 10 degrees C, which is the definition of polar. So either one of those would work to describe that, that pattern. Okay, so that's temperature. We're going to switch and talk a little bit about precipitation now. So maybe a good time to pause it, take a break, listen to somebody else for a second, and then come back and we'll talk about precipitation. Okay, so we're going to talk about both the amount and timing of precipitation and what factors kind of cause that variability. So some things that you probably remember from high school chemistry class or physical chemistry class in college are thinking about molecules and what happens to the movement of molecules with temperature. And so air temperature and the movement of molecules, kinetic energy of molecules increases with temperature. What that means is basically molecules are going to be moving around a lot faster when it's warm, and when it gets cold, each one of those molecules is going to be moving around slower, more and more slowly. What that results in is that when molecules are moving really fast, they tend to spread out. They're bouncing out away from each other. Molecules tend to move out and get less dense, right? So you know warm air rises. That rises because it's less dense and it's moving up away from Earth's atmosphere. So warm air rises because of that lower density. But then what happens as air rises? So we know that as you move up away from Earth's surface, the temperature decreases. And so the air is cooling. So air at Earth's surface gets warmed up. It gets lower density, it starts to rise away from Earth's surface, but it starts to cool and get more dense. The rate of cooling is referred to as the adiabatic lapse rate, and it's a little more complicated than what I'm going to tell you here, but this is a good kind of general rule for us, is that for every 1,000 meters you go up in elevation, the air temperature changes or cools by 10 degrees Celsius. And again, that has to do with the humidity in the air and some other things, but in general, that's a good rule of thumb. Okay, so we know warm air is getting less dense, rising. As it rises, it cools, gets dense again. The other thing that starts to happen as the air cools is that water, at some point, the water in that air is going to condense and fall out, right? So we get condensation of air. These basic principles that you've all learned before in some class or another all contribute to generating what we call the Hadley cells. So in this diagram here, we'll look at the globe here initially. These two kind of sets of arrows just north and south of the equator, these are the Hadley cells. There's these other cells, and here they're labeled as Hadley cells. Sometimes they're labeled as other cells. And so there's more of them than just the two at the equator, but those are the ones we're really going to focus on because those are the primary drivers of getting precipitation moving around the globe. So this picture, a little more on the right, is kind of a side view from Earth's surface, which is a little bit weird because I'm going to talk about air rising, so just be aware of that. But these black arrows here in these circular, in the oval patterns, those are representing the Hadley cells. So we have air that's sitting at the equator, let's say. We know air at the equator is experiencing less beam spread and less atmospheric scatter or interference. And so it's going to warm up more than the air away from the equator. As that air warms up, it's going to start moving away from Earth's surface. So these arrows are showing it moving away from Earth's surface. But we know it's cooling. At some point, the moisture in the air is going to condense and fall out as precipitation. As this air gets colder and colder, you would think it would sink back down because it gets dense, and it wants to, but new air is coming up beneath it all the time, and so it can't sink right back down. So what happens is it gets pushed out to the north and south. So that's why these arrows move to the north and they move to the south. And so new air is constantly moving away from Earth's surface at the equator. At some point, though, it gets away from that air coming up and it can sink back down to Earth's surface. Where it sinks back down, it's really dry because most of that precipitation, or a lot of that precipitation, fell out at the equator. And so the air coming down to Earth's surface is really, really dry. And so these Hadley cells tend to come down to Earth's surface around 30 degrees north and 30 degrees south. And so that dry air creates most of our deserts around those 30 degrees north and 30 degrees south. So I want you to be familiar with those mechanisms that contribute to the Hadley cells, and then think about also the patterns of precipitation that they create. Lots of rain at a lot of places in the equator, again, not every place, but lots of places, and drier zones at 30 degrees north and south. So this is just a summary of kind of those steps that occur during the Hadley cells. I won't go over it again, but it's there if you want it. And then here's a map of the deserts in around the world. And you can see not all of them are at 30 degrees north and south because there's other factors that cause air to be really dry, but a lot of them are. So here's 33, or not 33, here's 30 degrees south. So you can see a lot of the deserts in the southern hemisphere are occurring around that zone. And then in the northern hemisphere, a lot of them are around 30 degrees north. Some move further north, and we'll talk about that in just a second. All right, we'll talk about it right now. Okay, so the next effect, or the next thing that's causing variability in the amount of precipitation that falls on Earth's surface is the orographic effect. So oro is from the Greek word meaning mountain, and then graphy is just a field of study. So orography or orographic effect, orography is just the study of mountains. And it doesn't have to be climates, so that's the orographic effect is the effect of precipitation due to mountain ranges. So I won't go over this again, but just remember these same mechanisms we talked about, air moving up and cooling and the water condensing, those are going to come into play for the orographic effect as well. I don't have another picture. Let me see. I thought I did. All right, sorry, I don't have another picture. So I'm going to do it with my hands. Actually, I'm going to pause it and add one, and then we'll talk about it. Okay, see, if we were in person face-to-face, you'd be like, you would have to watch me to like draw this by hand on the dry erase board, which would probably just turn into a mess. So here's a nice picture of the orographic effect. So we can kind of imagine this as the Rocky Mountain range if we want to. Air coming from the western United States is forced up and over the mountain range. So in the Hadley cells, remember that warm air just rises up away from Earth's surface due to its low density. In the orographic effect, that's not necessarily the case. It's just forced up and over the mountains due to the movement of the weather patterns. But as that air is forced up, it's still going to get colder, it's still going to get more dense, and the water is going to condense out of it at some point. So as you move up in elevation, we get more and more precip falling out. But then as that air moves up and over the mountain range, on the leeward side or on the rain shadow side, there's no moisture in the air. There's very little moisture in the air. And so you get a lot less precipitation on at least in the Rocky Mountains on the east side than you do on the west side. Of course, it would depend on the direction of the mountain's range and the weather patterns. But in our case, we get more moisture on the western side than the eastern side, and certainly more at high elevations than at low elevations. So that's the orographic effect. Same general principles as in the Hadley cells, but just kind of in a different, kind of carried out in a different way. One thing I want to jump back here because of if we look at our desert map, let me see, let me get back there. Hold on. Here we go. If you look at our deserts, especially like our Great Basin Desert, is a result in large part of the orographic effect and less due to the Hadley cells coming down. And also in Asia, a lot of those deserts are due to orographic effect and not the Hadley cells. So you can see here that plays out in different places around the globe. Okay, so precipitation amount is driven in large part by Hadley cells and the orographic effect. And then the other thing I didn't really talk about, but coastal climates are often wetter, right? Because they're near the coast, the air is a little more moist coming off of the coast, and so that can then add more moisture to the air and more precipitation. But this is not a hard and fast rule. We'll talk about some exceptions at some point in the semester. I don't think necessarily today, or maybe I'll try to throw one in today. Okay, so let's just skip this for now and let's talk about the terms we're going to use to describe climate. I skipped some slides and I'm going to go back in just a second. Okay, so one of the terms we use for describing the amount of precipitation an area gets is arid. So an arid climate is a place where it receives very little precipitation. So for these terms on precipitation amount, there aren't as many good quantitative definitions as there are for temperature. So you can see the first bullet point there says precipitation is less than potential evapotranspiration. So that's a better way of defining dry or wet places than just saying it's less than 300 millimeters. You can see the third bullet point says arid climates are less than 300 millimeters. Well, you can have arid places that receive more than 300 millimeters, and you can have places that are not as dry that have less than 300 millimeters, okay? So the absolute amount of precipitation is not a great definer. It's okay, but it's not a great definer of how dry a place is. So this is where I skipped those slides. So I'm going to come back to them now to give you a definition of potential evapotranspiration, or PET. So I'll write it and talk about it as PET sometimes, or potential evapotranspiration. PET is the amount of moisture that would be lost from the soil and plants if the soils were saturated with moisture and plants were rapidly growing. So it's kind of like the maximum amount of moisture that could leave a system if there was plenty of moisture there. That's potential evapotranspiration. If the amount of precipitation you get is more than the potential evapotranspiration, you can imagine you got a lot of moisture in that system. You're getting more than that system could ever use. All right, so you've got excess water in that situation. So that would be a fairly wet place. a place that gets less moisture than PET is going to be limited by water to some degree. So it's going to be on the drier end of things. There are three factors that affect potential evapotranspiration: temperature, solar radiation, and wind speed. Temperature and solar radiation, we know, they're pretty well coordinated, except in mountainous environments. So those two are fairly similar in their effect. And then wind speed. The faster the wind speed, the more energy that wind has, the more it's going to pull moisture out of plants and out of the soil. And so hot, dry, sunny hot places that have lots of solar radiation and high wind speeds, they're going to have really high PET. So there's a lot of demand for water by the atmosphere. So aridity is really best determined by the difference between PET and MAP, or mean annual precip. So again, if mean annual precip is less than PET, we're thinking of it as an arid place. If it's higher, it's probably less arid and more mesic. So here, the two terms I'm really going to try to use are just arid and mesic. Mesic climates are often said to be places that receive 1,200 to 1,500 millimeters of rain, but again, they're really places that have more precip than PET. Right? So arid and mesic. I list xeric and steppe on here, and there's a reason I'll try to stay away from those more. Steppe really describes the vegetation of a place, not the climate, so we're definitely not going to use steppe. Xeric describes a strategy and a type of plant, not a species, but a type of strategy for growth that's related to aridity, but they don't really describe the same thing. So I'll try to use arid as much as I can. I'll probably slip up once in a while. Okay, that's the amount of precipitation. Let's talk about timing of precipitation a little bit. Okay, so we have, so this is just a different diagram of the Hadley cells. Let's do this one over on the right here because it's similar orientation to the picture we were looking at before. So we know that air is warming up the equator, moving away from Earth's surface, cools, and then water condenses and drops out near the equator. So when air is warmed at Earth's surface and then moves away from Earth's surface, it creates, you could kind of think of it that it creates a little bit of a vacuum, right? So you've got air molecules that leave. So if those air molecules leave, the pressure decreases at Earth's surface where that air left from. All right, so it creates a bit of a vacuum and lower pressure. All right, so that's a low pressure system, like where the Hadley cells kind of originate and begin. That's a low pressure system. So a low pressure system then is an area where the weather tends to be cloudy skies and have precipitation. That's what characterizes a low pressure system, because you have warm air leaving Earth's surface, water might condense and cause precipitation. So that's low pressure systems. On the other end of the Hadley cells where the air is coming down, we've got new air molecules forcing their way into the air at Earth's surface. And so we've got extra molecules crammed in there, and we have a higher pressure system. All right, so that air though is fairly dry that's coming down to Earth's surface. And so high pressure systems tend to be associated with clear skies and dry conditions. Right? So you've probably seen the weather maps before where the meteorologist shows the high and low pressure systems around the globe. That's my way of just trying to relate the mechanisms to those high and low pressure systems. So I do want you to remember what types of weather are associated with high and low pressure systems. There's just another diagram. If this helps you think about it and remember it better, great. You can use that. I have a couple pictures in here. I don't remember the first one, but the second one here, this was from a few years ago. I don't see the date, but I think it was maybe 3 years ago. When we were talking about high and low pressure systems, this article was in the paper, and so I highlighted it. Because there was a high pressure system sitting off of the West Coast, And it was this high pressure system, again, kind of clear skies and sunny conditions. It was blocking all of the storms coming off the Pacific from actually getting onto land. And those storms, California kind of relies on them because they blow away the pollutants and they can get a lot of the particulates out of the air if it rains. And the fact that these high pressure systems were just sitting there blocking those storms allowed the smog to build up. So this was actually, I guess, from, it says from Stockton to Bakerfield, the sky is thick with chemical laced particles. And that was because of that high pressure system. So just a way to think about how these systems are affecting kind of our lives and the lives of people around the globe. But let's just look at a map of high and low pressure systems. So this is a global map. This is average, like a 30-year average for January of where the high and low pressure systems generally sit across the globe. All right, so if we look at the U.S., in the southern part of the U.S., in January, we generally have a high pressure system. We have a high pressure system sitting off the southwestern part of the U.S., and then off the west coast here, we have this giant low pressure system. But then we know that Earth is tilting throughout the year, and that's changing where the warmest and coldest spots are. That also has effect on the high and low pressure systems. So here's July. If we look at the US, we can see there's a high pressure system sitting off the western US that kind of continues over the northern part of the US, and a low pressure system sitting over parts of the southwest. So, and I'll point these out from the Pacific Northwest. So I lived in the Pacific Northwest for a while in Oregon. And if you think about the Pacific Northwest and the weather, you probably think about like really wet conditions, and it's kind of wet and drizzly all the time. And that's true for about 9 months out of the year, or maybe 8 months. But the summers in the Pacific Northwest are really, really nice. They're generally like warm and sunny almost every day. And you can kind of see this with the high and low pressure systems. So if you remember, a low pressure system is associated with cloudy skies and precipitation or rainy conditions. And this low pressure system kind of flings those weather patterns onto the West Coast in January in those winter months. So that low pressure system is what causes those rains and those really wet conditions in the Pacific Northwest. But during the summer, we have that high pressure system that replaces that low pressure system and sits right on the West Coast, creating really nice summer and clear skies in the summer months. So just an example of how that can affect the seasonal pattern of precipitation. So we have kind of three terms we're going to use for defining precipitation patterns. Monsoonal climate describes an area that receives the majority of its rain in the summer months. The Mediterranean climate would be one where it receives most of its precipitation in the winter months. And then if it's neither of those, it's more of a uniform distribution, or we might say that the precipitation is uniformly distributed throughout the year. That means it doesn't really have a real dry season. And there's not a real simple way of defining these. Like temperatures, we can look at a temperature diagram and see it real quick. For determining whether it's monsoonal or Mediterranean, you have to do some more calculations. So I didn't give you a quantitative definition here, but you've done some of those calculations in the Köppen climate system. And so we'll see these calculations again throughout the semester. So this is what is defined in the Köppen climate system for monsoonal, is that the precip of your driest winter month is less than the precip of your wettest summer month divided by 10. So pretty complicated, right? But it's there if you want it. And you can see in general where our monsoonal climates are across the globe. Our Mediterranean climates then are the yellow ones. So you can see our west coast of the US is considered Mediterranean climate, as well as many of the areas around the Mediterranean. And there's your definition, or your quantitative definition of it, if you want to memorize that. Okay, so again, these are the terms we've talked about in this video. You need to be familiar with the mechanisms that these terms describe and the climate that they describe. So Hadley cells, oops, I'm going to get rid of one. Let's get rid of Coriolis force. We didn't talk about that. But for Hadley cells, you need to understand the mechanisms that create the Hadley cells. And then if we're talking about temperate or continental or tropical, you need to know like what is the definition of a temperate climate. So know those temperature zones if I gave them to you. If I didn't give you a quantitative definition, just know in general what it means. Okay, and we'll have an assignment where you'll have to do that, and so you'll get a feel for what I want you to know. All right, lastly, what I want to show you is the Whittaker diagram. So you've probably seen this before because we use it a lot in ecology. The Whittaker diagram was created in around 1975. Whittaker was working on this for a long time before this publication, but this is kind of his general idea of how climate impacts the type of ecosystem you would find in a particular place. So you can see on the x-axis here we have mean annual precip in units of centimeters. Just make note of that because a lot of times I'm going to talk about precip in millimeters, so you just have to move the decimal place over 1. And then on the y-axis we have mean annual temperature, but notice the coldest temperatures are at the top and the warmest ones are at the bottom. I think that's done just to create this nice shape maybe. You don't really need to do that, but that's often how it's presented. Anyway, this area that these two variables kind of create is, we would call this our climate space. This is the climate space of the globe right here, and this is the type of ecosystem we'd expect to find within these different climate spaces. So we're going to use the Whittaker diagram in your next assignment. You're going to have to kind of find out the climate of different regions of the globe and then think about what vegetation is most likely found in that particular region. So you'll be using this a lot, and I want you to become familiar with the Whittaker diagram. I'm not huge on memorization with these kind of things. I don't think it's useful to memorize it per se, but I want you to be familiar with it. Like if I were to cover up the names of all of these ecosystems and give you a word bank of the ecosystems, I'd want you to be able to place it there. So it's kind of memorization, kind of familiarity, right? So just be aware of that, being able to, that I want you to be that comfortable with this, this diagram. All right, so that was a long video. Sorry about that, but that covers all of the climate terminology. And then I'll have another relatively short one that's going to just define the different biomes that we'll be focusing on throughout the semester.